This video is for lesson 10-1, compositions of transformations. The learning goals are to find the image of a figure under a composition of rigid motions. That means a sequence of rigid motions. We're going to do more than one of these things called translations, reflections, and rotations. The second learning goal is to find the pre-image of a figure. So if we know the final image, can we go in reverse and figure out where the image was to begin with? Consider the series of transformations shown in the figures above. The first is, do you remember what capital R is? A rotation around the point 4, 6. That point is right there. And it's a rotation of negative 90 degrees, which is a clockwise rotation. So pay attention in this topic, especially to the sign of the degree of rotation. That's how you tell whether it's clockwise or counterclockwise. Now, it might be a little counterintuitive. A negative degree rotation is clockwise. The reason for that is that angles are defined like this. If we have a side of an angle and then we lay one right on top of it, that's a 0 degree angle. If we go up a little bit like that, maybe that's a 1 degree or 2 degree angle. If we make that angle a little bit bigger, right? Maybe that's now, I don't know, 30 degrees or something. So as you expand the size of the angle, you're doing it by moving the ray in a counterclockwise motion. And these create positive angles. So we use a positive degree for counterclockwise rotation, and we use a negative degree angle for clockwise. So that's something we have to be careful with. The second transformation is, do you remember the lowercase r? That's a reflection over the line y equals 0. So the line y equals 0 is this horizontal line running right on the x-axis. We're reflecting that arrow to the other side of the line, and it ends up here. Together, these are a composition of transformations, or a sequence of transformations. The notation for a composition of transformations is similar to the way you express compositions of functions in algebra class by putting one of the functions kind of inside of the other. Let me show you a quick example of that. Let's say we had function f of x, and we might put that like inside of function g. Does that look familiar to you? That was a composition of functions, combining functions together. The composition pictured above is described as the reflection over the line y equals 0 of a negative 90 degree rotation around the point 4, 6. So it's like this rotation is put in parentheses and then the reflection is applied, kind of like how the f of x is put in parentheses and then function g is applied. If a reflection across the x-axis were added as the third transformation of the sequence, then the notation would be reflection over, this was supposed to be the x-axis, so that's y equals 0, of the reflection over y equals 0 of that rotation. So look at the sequence of 3 transformations kind of building out from this happening first, then this happening, and then this happening. It's almost like you can read this backwards to see the order that the transformations occurred. Notice that the transformation that occurs first in the series is in the interior of the notation, and subsequent transformations are written outside of it. Let's do some samples with this. Number 1, write the notations for these compositions of transformations. Use the points A at 0, 0, B at 1, 1, and C at 0, -1. Question A clockwise rotation of 60 degrees about the origin. The symbol for rotation is a capital R. As a subscript, we put its center. In this case, it's the origin. So that's either point A because that's 0, 0, or we could say 0, 0, the origin, comma, and then we put its degrees of rotation. It says it's clockwise 60 degrees. That's a negative 60 degree angle. Again, we have to be careful about Clockwise rotations are represented with negative angles in algebra class. Counterclockwise rotations are represented by positive angles. All right, that was the first in a sequence. This is followed by a translation. So we're going to put this in parentheses. And now the symbol for translation was a T. And then it has a subscript indicating what you are translating along. In this case, it's along the directed line segment AB. Now I could, as a subscript, write AB with the segment on top, but because this is coordinates, we can do better than that. A to B, let's look what happened to the X value. From A to B, the X has increased by 1, and from A to B, the Y has increased by 1. So we could, as our subscript, indicate that our transformation adjusts the X coordinate by 1 and adjusts the Y coordinate by 1. So I'm not saying the point 1, 1. I know that's confusing. This looks like an ordered pair, but I know it's not a point because I have the transformation symbol. And this is saying increase X by 1, increase Y by 1. So there is our composition. The rotation occurs first, followed by the translation. Question B, a reflection about the line X equals 1. So the symbol for reflection was a lowercase r, and then its subscript is the line that you're reflecting over. X equals 1, like that. And then it says, followed by a reflection about the line X equals 2. So let's put this in parentheses and indicate that we're taking this image and reflecting it. So another lowercase r, X equals 2. Again, I'm working here, putting parentheses around it, and then I'm working towards the left. I'm building it out towards the left. Okay, question C. Let's do 3 translations, each of the directed line segment AC. So the symbol for translation is a capital T. Now I could say segment AC, but because it's coordinates, we can do better than that. From A to C, the X coordinate doesn't change. So you're adjusting the X value by 0. From A to C, the Y value decreases by 1. So -1. Again, this does not mean the point 0, -1, not for a translation. These numbers are telling us how to shift the X coordinate and how to shift or slide the Y coordinate. Okay, that's our first of 3 translations. So we're supposed to do this again. So I'm going to put that in parentheses and then take that result, that's some sort of picture, take that image and translate it. Again, by adjusting X by 0 and Y by -1. I'm not done. We're supposed to do 3 translations. So then this whole thing goes in parentheses. And then one more time, let's indicate that we want to translate that 0, -1. The figure shows an arrow that points from a short horizontal line, that's this thing here, through 4, 2, to its tip at 4, 10, right there. Number 2, draw the image of the arrow mapped by the composition, a reflection over X equals 4 of a 90-degree rotation around 4, 0, and label this A. Okay, so we're going to work from the inside out. We're going to work kind of from right to left in a sense. So let's start by finding 4, 0. 4, 0, right there. We're going to rotate around that point. 90 degrees, so positive. What direction of rotation is a positive angle? Counterclockwise. We're taking that arrow and twisting it that direction. Counterclockwise, 90 degrees. Let's draw what it would look like. So that's going to go to here, and then across to here, and here like this, and then the shoulders of the arrow, and then the point of the arrow, right there. That handles this piece right here, the rotation. Now let's take that image in purple and reflect it over the line X equals 4. So let's think about the line x equals 4. It crosses the x-axis at 4, and it is a vertical line, like that. We want to reflect the purple arrow to the other side of that line. So now it's going to look like this. And then across here, now the little shoulders of the arrow, and now the pointer part of the arrow. This arrow on the right is the result of this composition or sequence of transformations. We're told to label this A. Okay, so A, this is figure A. Number 3, draw the image of the arrow mapped by a composition of the same transformations, but in the reverse order. So the first thing we're going to do this time is the reflection across x equals 4. So x equals 4 is this line here. We want to reflect that arrow across the line. Because that is a line of symmetry, when you reflect the arrow, it's going to land smack dab right on itself. It's kind of interesting, huh? Then let's do the rotation. So that arrow is going to rotate and land here. Label that figure B. Question 4. What single transformation maps the arrow to image A? Write the name of the transformation and its symbolic representation. So if we wanted to take the original arrow that was in black ink and in one step create this picture in purple, do you see how we could just have done a clockwise rotation of 90 degrees? And so it says what transformation? It would be a rotation or a clockwise rotation. And we're supposed to give it symbolic representation. So capital R is for rotation. And then what are we rotating around? We're rotating around the point 4, 0, comma, and now the degrees of rotation. A clockwise rotation is a negative degree angle. Like that. Question 5. What single transformation maps the arrow to image B? So the original black arrow, if we wanted to take it to figure B in one step only, how about a counterclockwise rotation of 90 degrees? And so we have R for rotation. We're still going around the point 4, 0, but we want to do a counterclockwise rotation, which is a positive degree measurement. There it is. As demonstrated in those items, the order of transformations in a composition can affect the position and orientation of the image. And as shown by items 4 and 5, a composition can produce the same image as a single translation, reflection, or rotation. Number 6, for each of these compositions, predict the single transformation that would produce the same image. We have a sequence of translations. Again, these are not ordered pairs in the case of a translation. This is telling us how to shift the x and y values of points. So let's work our way from the inner parentheses outward, or in a sense, we're working from right to left as we do these translations. So let's think about what each of these things are going to cause to happen to a figure or to a point or whatever. 1, 0 is going to cause the figure to move one spot to the right, but up or down nothing. Then 0, 1 is going to cause the result right here at the end of the first transformation to move left or right nothing, but up 1. And now we're right here. And then this third translation is going to cause the x to move by 1 and the y to move by 1. It's going to cause it to go 1 to the right and 1 up. Here was the original point. Here's where the final image is after the 3 slides. So what single translation would produce this same final result? So T for translation. It looks like if we move the x 1, 2 to the right, and we move the y value up 1, 2 up, that would get us from the original spot to the final step with a single transformation. So there is the single transformation. Question B. Let's rotate 90 degrees around the origin of the rotation of 90 degrees around the origin. We're doing two rotations. So let's say that this is the origin right here, and that there's some point somewhere. For instance, right here, just as a sample to try to keep track in our heads of what's going on. 90 degrees, a positive angle, is a counterclockwise turn. So 90 degrees, this dot is going to rotate to there. And then this image, what we're doing to it is rotating it 90 degrees. So continue in a counterclockwise direction until it gets right there. So here is the original point. After the two rotations, it ends up here. What single transformation would have done this? One possibility is to rotate it around the origin 180 degrees. Question C. Let's reflect across x equals 0 this. And this is the reflection across y equals 0. So let's do a quick sketch to see what's going on here. Here we have a x-axis and y-axis. Really quick sketch. And let's say we have some point like right there to begin with. If we reflect it over y equals 0 is the x-axis, it would pop over to that side. And then we're going to reflect that over x equals 0. X equals 0 is the y-axis. It would pop over to there. What single transformation would get that original dot to end up right there? There's a couple possibilities, but one way to accomplish this would be if we rotated that dot 180 degrees around the origin. That's one possibility out of several. So we want to rotate around the origin 180 degrees. Next, use this figure for items 7 through 9. I see an arrow, and then there is a transformation, and then it looks like this. Number 7, identify a composition of transformations that could map the arrow on the left to the image on the right. How can we make this look like this with a composition? What could we do first? What could we do next? Well, one possibility is to rotate that so that instead of pointing to the right, it points down. If we could get it to rotate around that point right there, we could make it look like this. Once you have it pointing the correct direction, couldn't we then slide it downwards however far we need to? And so our first step might be to do a rotation around that point. That point is 0, 6. And the rotation that I did was to turn it clockwise 90 degrees. So negative 90 degrees. Ooh, sorry about that terrible writing on that. And then I'm going to put that in parentheses and now apply a translation, a slide. So that's going to be a capital T is the symbol for translation, and I want to indicate how I'm translating it. We don't need to move it left or right at all, so we're adjusting the x coordinates by 0, but we want to slide it down from the 6 down to the origin, right? So that the arrow is right there at the origin. And so we want to slide it down 6. So here is a composition that would make that black arrow end up like that arrow. It's not the only possible answer, but it's one that works. Number 8, consider the composition we identified in item 7, but with the transformations in reverse order. Does it still map the arrow to the same image? If we did the translation first, if we slid the arrow down first so that it ended up down here, and then we rotated it around 0, 6, would we get that? And the answer is no, not if we rotated it around 0, 6. Now if we rotate it around 0, 0, it would end up in that position. But the answer is no, not with 0, 6 identified as the center of the rotation. Number 9, identify a composition that undoes the mapping, meaning it maps the image of the arrow on the right to the pre-image on the left. How can we get that arrow to be up there? Well, again, there's different possible answers, but we could first rotate it counterclockwise 90 degrees to get it to look like this. And then we could do the slide upwards to get it to the proper height so that that is at the 6. Let's write that out using the symbols. So we want to rotate, capital R, and we want to rotate this around the origin, 0, 0. Counterclockwise is a positive angle, so 90 degrees. That gets the thing turned and pointing to the right, and then we want to translate it upwards. So we want to slide it, translate it up 6 spots. So 0, 6. You can also find compositions of transformations away from the coordinate plane. Number 10, points A, B, C, and D are points on this arrow-looking shape. Predict the direction of the arrow after it's mapped by these compositions. Again, remember to work from the inner to the outer, or another way to think of that, work from right to left. Let's first translate this weird-looking arrow figure with these little tails on it. Let's translate it along segment AC. So the directed segment from A to C, we're going to slide that arrow down this far. And then it would exist, down here on the paper. But keep track of where it's sliding to and if the direction of the arrow ever changes. Simply sliding the arrow doesn't change the way that the arrow points. And then we want to slide it along segment DB. Well, segment DB goes from here to here, so it's like sliding it to the right. Sliding it down, sliding it to the right does not change the direction that the figure points. So I think it's still going to point to the right. Okay, this one here. First, rotate it around point D. Right there, point D. Rotate it 90 degrees. Okay, 90 degrees, a positive angle, is a counterclockwise rotation. If we rotate it, it's going to point up. Keep that in your mind. It's going to point up. Next, let's reflect it across segment D prime, B prime. Well, where is D prime, B prime? We rotate that thing, then point B, as it turns, is up here, B prime. And we want to reflect it across that segment. Well, if the arrow, let me quick draw one, is looking like this, and we make a segment which is like a line of symmetry of the arrow, and we reflect it, the arrow itself still points up. And so I think that arrow figure is going to point up. Next, reflect across segment AC. What's that going to do to that arrow? It's going to flip it and make it look like that. Then do a 180-degree rotation around point A. Take that arrow, and point A is, kind of just right up above it, right? And rotate that thing around 180 degrees. What's going to happen to the direction that it points? It's going to point to the right. These problems can be tricky to keep track totally in your head of what the figures look like. So little sketches like this, or even much nicer sketches where you're retaining the exact size and shape of the object using a ruler, might be needed to accurately predict the final results. Like many functions, transformations have inverses, which are transformations that map the image back to the pre-image. The inverse of transformation T is designated T, and that it's almost like an exponent, but it's not an exponent when you're talking transformations in geometry class. So T with a -1, that's the symbol for the inverse of T. t with a -1 superscript. It has the property that when you apply that transformation to that transformation, you get the original pre-image. They undo each other, creating the original image. The table lists the general formulas for the inverses of translations, rotations, and reflections. So the translation over directed line segment AB has this notation. We learned that a couple of videos ago. And its inverse, taking that transformation, sticking a little -1 there means to do its inverse, could be shown as translating over segment BA. Doing the directed line segment in reverse would take you back to the original picture. Reflection about line L looks like this, again a couple of videos ago. The inverse of the reflection over line L is to do another reflection over line L. If you flip something over a line and then you flip it back over that same line, you'd get the original picture. Does that make sense to you? The rotation of m degrees about 0.0 has these symbols, and so its inverse of that would look like this. Just do the angle in the opposite direction. So if m was a positive degree angle and then you rotate it the negative of that angle, that would take you back to the original picture. Here are some check your understanding questions, so I will pause the video. So the goals that we worked on here were to find the image under a composition of rigid motions. Can we do more than one transformation in a certain sequence? And we also worked on finding the pre-image under a sequence of rigid motions. Knowing the final answer, can we work in reverse to find the original answer?